Good afternoon, everybody. And I'm very happy to welcome you to this public lecture by Professor Cumrun Vafa. And this is the beginning of a long relationship between the ICTS and the Indian Institute of Science. And this public lecture is part of the joint program between the two institutions. So I'm extremely happy to announce that to you. And now, I think Cumrun Vafa is here just by accident. I mean, he's a very good father. His son is visiting Bangalore, and so he came here, and it's wonderful that he could spare time to visit us today. He's, as you know, one of the most eminent and leading string theorists in the world today, and he's done a professor of science at Harvard University. Cumrun Vafa has made many seminal and path-breaking contributions to string theory, quantum gravity, quantum field theory, and mathematics. And I will not name all of them except mention to you that his work with Andrew Strominger on the exact calculation of black hole entropy in string theory is a major landmark, not only in the subject, but I think in all of theoretical physics, because in some sense it unifies disparate knowledge. It unified the idea of entropy of a black hole, which was a geometric object, with the definition of entropy introduced by Boltzmann, which is just a counting problem. And so in that way, gave a lot of support and solidity to the fact that quantum gravity has new and additional degrees of freedom which contribute to the entropy of a black hole. And I think this paper is perhaps one of the most important works in the subject of string theory. He has also made a very important contribution, pioneering contributions to the very mathematical subject of mirror symmetry and also topological string theory, which has also had impact in pure mathematics. He is a member of the National Academy of Sciences of the United States, and he was awarded the Leonard Eisenberg Prize for Mathematics and Physics in 2008 of the American Mathematical Society, and the very prestigious Dirac Medal of the ICTP in 2008. So with these few words, I'd like to invite Cumrun to the stage. And present for you. It's kind of you. Yeah. So.
Oh, wow. That's very kind. I'm moved. Thank you.
So I invite him to now deliver his public lecture.
Well, thank you, Spento. It's a very kind introduction. And I think it's not completely accurate to say that I'm here by accident. I think there's a truth to the statement, but I think that I'm from Iran originally, and I have always wanted to visit India. And there have been a number of occasions which I almost managed to come here, but they never materialized. And a few times Spento had suggested I could come and visit, and I grabbed this opportunity to come here. So it's not quite accidental, but anyhow, I'm very pleased to be here and to be in India and also to be giving this talk. Thanks for the invitation. So I'm going to talk about some general aspects of string theory, and I'm assuming that many of the people here may not be string theory experts and may not even be physicists, I don't know. So I'm assuming that it's a general audience, so that's what I'm gearing my talk towards. I hope it's not completely inaccurate. In case you're expert, I apologize in advance. So I start from the very basics of physics, perhaps perhaps let's start here. I guess we can go further back, but let's just start with Newton as initiation of modern physics. And, well, in some sense, a lot of things start here, namely the falling apple, as is well known. And so what we learned from the studies that Newton and previous physicists studied, like Galileo and others, that we can describe a lot of things using classical mechanics, using simple laws of classical mechanics, in particular trajectories of particles, or even how the planets work, or how the apple goes around the planets, and so forth. These were all very elegant and simply described by Newton, and things look very nice and solid and elegantly put in place. We describe all these planetary motions, this and that, and even the same equation that described Newton's description of gravity for our solar system applies to faraway galaxies and things that they didn't know at the time of Newton, but they have checked and it works according to Newton's equation. So things are very beautiful and solid. And the underpinning of all these discussions involves a description of space, which is what we call a flat space, which means, you take a Cartesian coordinate x, y, and z, and so forth, and you describe it in this way. And Newton's description is sufficient with this kind of geometry to describe all these beautiful physics. So this is the kind of the classical physics, and then this guy comes along, and well, he tells a few things to us. He tells us that, first of all, description of the space in terms of the three spatial directions is not sufficient. We have to add time to the discussion. And moreover, the space is not the same flat thing that Newton was imagining. So the space became a little bit curved, and geometry of space and time is put together in a curved four-dimensional space. Oh, cell phone. Good point. Maybe. Yeah, it is. I'm moving it and it makes more sound. I'll put the cell phone here. Thank you. Okay, so that's what we learned, that we have to pay attention to space and time and the fact that they're both together curved. And the curvature of space-time affects how we think about the property of gravitation and how the particles move in the near gravitational fields. We think about the gravitational fields as the matter as causing curvature in space-time, and the particles are moving in geodesics, in shortest distances in space-time, and that is why the particles appear to be going in curved directions, like the planetary orbits. So if you have curvature in this space, things which start looking parallel may end up attracting or going in a different direction depending on what's the curvature. And so this description of what happens if you have a curvature in space and what appears to be straight lines will may deviate from looking as maintaining the same distance and appears as attraction. So this notion that you can have an appearance of force from pure geometry is, I think, well exhibited by this picture. So this was basically a geometrization of physics. So Einstein's, I think, fantastic work was not only to have a more accurate description of the phenomenon of gravitation, but to geometrize it. And I think that's the most elegant thing that happened in that theory. And in fact, the bending of the light as it passes through heavy or massive objects is one of the main things that he discovered, and which was predicted according to his theory and confirmed by experiments as one of the first experiments to have confirmed this theory. And similarly with the planetary motions. And in fact, what's amazing is that this theory of Einstein is applicable not only to the individual pieces like Newton's does, but also to the whole cosmos as a whole. And the phenomena of, for example, Big Bang and so on are well described by Einstein's equations. So it's a very elegant geometric description of the full universe, and it's quite remarkably powerful. So that was quite a nice story, except the story never ends, and comes along the fuzziness that was introduced to physics in the context of quantum theory. So when we went to study shorter distance scales, we find that the matter are not given by particles, point particles the way we are used to, but the point particle itself is kind of spread out in terms of some particular clouds of what we call the wave functions of the particles, and this fuzziness is the beginning of this quantum description of nature. So quantum mechanics was born by trying to describe this, and it was a little bit unsettling because a lot of the laws that everything that we're used to in the context of classical physics are deterministic, but quantum mechanics comes along and tells us that there are things which are not deterministic. One of the main pioneers being Niels Bohr, and the ideas that quantum mechanics brought along was so radical that even Einstein was intrigued, and there was heated debates of whether this is the right way to think about the physical laws and physical realities. And today, after the passage of about 100 years, we still have nothing better than quantum theory to describe reality, and still stands as the correct description as of now of what we think is going on at atomic scales and beyond. So that's the kind of story we learn. So we have the principles of quantum mechanics valid not just at atomic scales, but also at subatomic scales. So these are, if you think about this as a caricature of an atom, the nucleus of the atom itself is made of quarks. And so we think about the electrons and the quarks as being elementary descriptions. And so kind of we now think about this whole collection of particles as unified into one description involving what we call the gauge forces and what constitutes the forces between them. And the gravity stands out of this picture and somehow separate and not being as part of this simple description. So except for gravity, the rest of the particles and forces are very well described. And in particular, ideas from particles and description of forces in terms of exchange of particles has been checked to a high energy, to a high accuracy in high energy experiments and accelerators that have been detecting them. So one of the main proponents for these ideas of trying to describe forces in terms of particles and the exchange of them is Feynman, and the basic idea that the particles come along and exchange another particle as being the reason that there's a force between them is by now a standard paradigm of physics and particle physics. We can have all the other processes where electrons and anti-electrons, which are positrons, come along and they exchange photons and they go their way. And so there are various different ways of trying to think about these kind of diagrams and processes depending on how many loops they form and so forth. They can exchange all possibilities, and Feynman's statement was that anything that can happen does happen in quantum theory, and so you have to sum over all possible histories that a particle could have, and that's the fundamental description of quantum theory, sum over all path histories of the particles. So we have on the one hand quantum theory together with particles and the forces between them, which are unified into one object, and then on the other hand gravity, which is given by this beautiful theory of Einstein's. And since quantum theory is believed to be true because it describes at least the subatomic physics, and since gravity of Einstein's gravity seems to be true because it certainly describes the macroscopic description of the force involving matter, then they should be both true, because you cannot have a universe with two laws which are not compatible. But it turns out that when you put the apple, the gravity one with quantum mechanics symbolized by this Planck's constant h bar, when you put them together, you get disaster. I'm trying to depict disaster here. So you get singularities. You try to do computations, and the computations blow apart. They get infinities in the middle of your computations, and it doesn't make physical sense. So this dissatisfaction of Einstein's of quantum mechanics was somehow reflected in his not a happy marriage between this gravity theory of his and quantum theory. So So what do? Well, guess what? Strings come along. So these are new ideas which come along as describing the fundamental entities not as point-like object, but as a loop or one-dimensional objects, as replacing the fundamental entities of nature. And so we think about strings as the fundamental building blocks of matter. Now, why did we think about this? Well, we just slept one night and then we came up with this idea. Not quite. People were trying to do some computation and they didn't know how to do it in terms of describing some scattering of particles in the accelerators. And somebody said, well, this formula looks cute. Somebody just wrote down a formula. And then someone said, this formula looks bizarre. How do you get such a formula? It says, well, it looks like it has some oscillations in it because there are infinitely many particles and it seems to be there. And someone said, oh, it sounds like maybe it's strings. And then they studied string theory from that. So it was a very bizarre beginning. It wasn't like, let's try to solve the consistency of quantum theory and gravity. But nevertheless, no matter how we came up with this, string theory turns out to be the solution to the big puzzle of trying to find a unified framework of trying to unify gravity with quantum mechanics. So basically the idea is that we replace the point particles like quarks with one-dimensional object like string. Of course, it doesn't mean that the quark is huge. What I mean is that if you take, in principle, a magnifying glass and zoom in, then this looks like actually not a point-like object, but a string-like object. Of course, this size could be very small. It could be very tiny. Perhaps even as small as 10 to the minus 33 centimeters. So we don't really know exactly what the scale is, but it's much smaller than nuclear scale, the scale that we see for the quarks and nuclei. So one way of thinking, therefore, is that these quarks that are constituting the nucleus of atoms are actually made up themselves of these strings when you magnify them. And the string interactions are again given by exchanges of strings instead of particles. So instead of particles going and exchanging particles, strings go and exchange strings. Of course, this sounds natural. After all, Feynman's idea that the sum of all possibilities will involve the exchange of all possible strings, and this is consistent with that picture. So this is just replacing the particle here exchanged with the exchange of the string. So here you see that you can think about these two strings coming along and making one string. And so two strings joining together as an interaction of strings. As you can see, this picture looks familiar, especially if I rotate it the other way. It looks like a pair of pants. And this is called the pair of pants diagram. And what's elegant about it is that even though it looks like there's some particular special point where the strings come together, that depends on how I slice the pants. So it depends on how you what slicing you take of the pant. There's no specific point where you can say the strings joined. All you can say is that far away they look like two strings, down here they look like one string, and somewhere they met, depending on how you slice it. So in some sense, it smooths out the interaction between the strings, and this smoothing out was the reason, what's responsible for getting rid of the infinities I was alluding to. The reason that the quantum theory and gravity were not working well for point particles is gone here because of this spreading of the way they interact in this smooth way. And as you can see, the topology of this interaction, the way they come together, encodes the interaction in terms of these pairs of pants diagram. So you can think about it in this way. The two strings come and join and form one string. Of course, you can go the inverse way, a string coming and splitting into two. And every interaction of string theory is simply given by this. So you can combine these pairs of pants and form more complicated interactions. So you can get description of them. In fact, more is true. That is, all the possible states of matter we have, like electrons, quarks, and so on, all are given by different states of the string, different vibrational modes, and different kinds of geometries that these strings are in, would constitute having different properties and describe one of them becomes electron, one of them becomes quark, one of them becomes photon, and so forth. So you can describe all these elementary particles as different excitations of this string. So it unifies not only the forces in this way into one entity, so it unifies everything together in a very elegant fashion. This picture was taken in our laboratory of the two strings, which, no, I'm just kidding. So it looks very experimental, but it's just still a visual experiment that you can see the strings coming and joining and then now going to two other strings. So this is the joining and splitting of two strings. Again, as I said, you can have, as I mentioned, you can have interesting geometries. Again, the string splitting to two and going to another one. So you can get a donut-shaped object, or more generally, you can get arbitrary number of handles or holes in your geometry, depending on how the strings interact with each other. So as you can see, it's a beautiful, simple geometry involved. So here is the description of, again, two strings coming, joining, and then going out. Now here you see I don't draw where they split and join, because that's up to you how you want to describe it. All you can say is that there are two strings coming and two strings going out, and they form one whole. So you have to, in principle, if you want to consider scattering of these two strings and going to two other strings, you have to sum up all possible ways that the strings can come and join, which means in principle you have to sum over all possible surfaces with arbitrary number of holes. And once you come up with summing of all these amplitudes, you find the probability for this to happen, as in Feynman's description of quantum theory. So this is a beautiful merging of physics with geometry of these surfaces. So here is basically where we are at. The solids are made of atoms made of electrons and nuclei are quarks, and quarks are strings. So we are basically have this overall picture of how these all work. But now, what we have added here is that everything is string, number one, and secondly, all the interactions of the particles are simply described by this simple pairs of pants diagram. Very simple. So it unifies not only the particle, but also the interactions. So strings is the prime candidate for quantum gravity, but there's some problem here. The string geometry connection starts on the wrong foot. So I'm advertising the strings as having an amazingly rich geometry, but actually there's an embarrassment. String theory demands that the dimension of space-time is not 4, as Einstein thought, but actually 10. Slightly miscalculating the dimensions here. 10 instead of 4. Well, on the positive side, you're predicting the dimension of space-time, where Einstein just put it by hand. String theory is predicting the dimension. That's an advantage, maybe, but it sounds like a wrong dimension. So it predicts the wrong dimension somehow, so this is a little embarrassing. And we have to get rid of these 6 extra dimensions. And that was a dilemma that string theorists had to face for a long number of years. And they found a solution. The solution was, what if these 6 extra dimensions are so tiny you can't see them? Isn't it funny? It sounds funny to you, doesn't it? It didn't sound funny to us back then. But it sounds a little embarrassing. It sounds like the number of angels on the head of the needle or something. It sounds a little bit strange, but you kind of get rid of it. This is not like usual physics. Physics, when you have something extra, it's something good for something. Here we say, well, just take them small and tiny and don't see it anymore. Doesn't sound too good. Doesn't sound too good. And I'm with you on this now. But this is not satisfactory, as I said. And this is the question that we always ask in physics. Whenever you get a new element in physics, you ask, what is it good for? And if you don't find a good answer to that, then you get doubtful about this new concept. So we should be asking, what are these dimensions good for? Not how to get rid of them, as was the original viewpoint on them. So here, I want to basically go over a list of issues that have nothing a priori to do with string theory, but are puzzles of 4-dimensional physics. I want to tell you the puzzles of 4-dimensional physics and what happens to them in the context of string theory. So one puzzle is a black hole entropy. So Bekenstein and Hawking found a formula which suggested that the black holes have some number of degrees of freedom, which in other words makes the black hole as having some entropy, which is proportional to how big the black hole is, and more precisely what is the area of the horizon divided by 4 instead of the entropy being 0. Now, Einstein's theory, if you count how many black holes there are, it turns out there is a unique black hole for a given mass and charge, and therefore the entropy is 0 because there's a unique solution. And that was disagreeing with Bekenstein and Hawking's computation, which used the semi-classical arguments to derive the formula for the black hole entropy, which suggested that the black hole of entropy is huge and given in some units by the area of this huge black hole. So that was a puzzle. What do these degrees of freedom mean? Because Einstein theory doesn't have that. Where do the degrees of freedom black hole reside? Einstein would have said there's no room for it. Next question is, what dictates the structure of matter? We know that we have, for example, quarks, but not only that, we seem to have 3 copies of quarks. Quarks, light quarks, mirror quarks, and big quarks. It sounds like this story, the little bear, big bear, etc. It's true. We have 3, this is not a joke, we have 3 families of quarks, the little one, the middle one, and the big one. And we could ask why, and there's no good answer in the context of particle physics. And not only that there's no good answer why there's 3, is why is there any conceptual framework which suggests that there could be an answer other than 1 or none? Why should there be 3? Or how could there be other than 1? And then what are the type of forces between them? And what are the forces that we are seeing? Now another question, again in the context of 4-dimensional physics, these questions arise. Again, nothing to do with string theory, just 4-dimensional theories. So when people were studying 4-dimensional theories of the type which describe particles and forces, they ended up to use auxiliary spaces to solve these interesting quantum theories in 4 dimension. Out of nowhere, they would introduce objects, for example, of a torus. They were trying to solve a problem in 4 dimensions, and they said, well, it would be nice if I pull out of the hat some other space which has nothing to do with 4 dimension, which is useful in solving this problem in 4 dimension. For example, a torus and a donut-shaped object, and Montana and Olive, for example, introduced this in trying to solve some of these problems. Why? It wasn't clear. It sounded like it has some interesting properties. And similar theories appearing later on in physics. In addition, it turned out that the monopoles and dyons, the particles that you could get in these theories, could be viewed as some strings wrapped around these donut-shaped objects. But again, this donut was not part of the space and time. Nevertheless, this auxiliary space somehow was useful in solving the 4-dimensional quantum field equation. Very bizarre. So, a priori, nothing to do with higher dimensions, but just an auxiliary space which solves the problem at hand. Now, in solving these quantum field theories, one ends up occasionally, very often, of encountering a situation where the forces become very strong. This happens in the context of nuclear physics. The forces that binds the quarks in the nuclei is a very strong force, and whenever we get these strong forces, our computational ability breaks down typically, because usually we have some small parameter where we use a small parameter as a way to control the computation, as a step-by-step correction to a computation using a small parameter, what's called perturbation theory. But this doesn't work when you have a big parameter. When you have strong interactions, these parameters are big. What replaces this notion of a small parameter in these contexts? Again, a question that we encounter in the context of real-world physics, like the forces that we see in the nuclei, but there is no simple description about how we should think about them. So, as I mentioned, until the mid-90s, the extra dimension of string theory were viewed by and large as an embarrassment and at best a tolerable feature. So we would be trying to say, well, the space could be this and that, and maybe it has, what we call compactified into these small pieces where everyday experiment doesn't see them. And so don't bother with them. We just think about the big space, which is the space-time that we live in. Mathematically, logically, it's possible, but is there anything else that you can say about this space, or is there anything else that they bring to the table, Are they useful for something else? So it turns out that this story changed dramatically with the discovery of string dualities in the mid-90s. So string dualities is, in my opinion, perhaps the most fundamental discovery the physicists have made in a century. It's one of those things that I think our generation of physicists will be remembered for long later, after we're gone. It's one of the most important discoveries, even though yet we have not connected it with experiments. And the string dualities, which we have discovered theoretically, have an amazingly powerful aspect to them. And it turns out that these dualities have shaped a lot of the modern physics in the past couple of decades, or past 15 years or so. And the basic statement is this, that you start with a physical theory which depends on some bunch of parameters, and you change the parameters from one region to another, and you get a different string theory. So you get a different, originally we had a bunch of different types of strings, and it turned out all of them were related to each other by changing of these parameters into one object. So it unified different objects into one. And this is what was later called M-theory. And it turns out that we learned that not only strings are there, but also other extended objects like membranes, instead of being one-dimensional, being two-dimensional, or more generally being higher-dimensional, which we call them branes, generalizing the notion of membranes to higher dimensions, they turn out to play a key role. So we found that the theory we were describing was not a theory just of one-dimensional strings, but higher-dimensional membranes as well were part of the discussion, and that was an amazing discovery. And in fact, it's good to bear in mind a familiar analogy. So we have different phases of matter, like liquid, gas, and solid, and if you look at a liquid and a gas, they look very different. But it turns out that, and this was the case for strings, we had a bunch of strings which looked very different from one another, but it turns out that the liquid and gas, even though they look very different, if you change some parameter, they can be looking like each other. For example, you can change the temperature and pressure along the path I have indicated here, and you can go continuously from a liquid phase to the gas phase without ever crossing any particular phase transition. So you can avoid phase transition by going this path, and you can continuously go from one phase to another. So there is no way you can distinguish them in this continuous parameter. So by gradually tuning this parameter, what is liquid becomes gas. Of course, they look very different, but there is no fundamental distinction between them once you go through this path. And this is what happened in terms of strings, string dualities. That is, we had a situation where they look completely different. One looked like a liquid, one looked like a gas. And we changed some parameters, and they became the same. So we learned that two things which we thought had nothing to do with each other were actually the same object, but you could only see it if you changed the temperature and pressure appropriately. Not only that, we learned that as you change the parameters in this theory, even the dimension of the space changes. For example, we thought about the strings, for example, like this, as going from one part of the space to the other. And as we changed these parameters, it turned out the space grew a dimension. By changing the parameters, so let me go back. So we thought the string was one-dimensional, and then as we change this parameter, we said, oh, no, there's some other dimension coming to play, which is this thickness in this other direction. And by the way, the string became a membrane, which is one of the motivations for calling this M-theory, which you can actually, string being one-dimensional was actually a mistake, was actually a higher dimension yet. So it depends on what kind of parameters you're choosing. So in some limit, it could look one-dimensional, and in some other limit, it could look two-dimensional. And the dimension could be 10-dimension, or it could be 11-dimension. So the dimensions and the sizes of the objects and the branes just became a tunable parameters, depends on how we look at it. So also we found that not only that, we have different kinds of strings in different theories. One string was a light, fluffy string like this green one, and one of them was this heavy, hard-to-move strings. And if you change parameters, they exchanged roles. One of them became the nice, fluffy string, and the other one became this heavy, unmovable string. So So we learned that what played the role of light, fluffy, became the other way and vice versa. So and the notion of what is light and fundamental became heavy and composite from the other perspective. So the notion of what is fundamental particle or fundamental string depended on what range of parameters we are dealing with. So string dualities told us that there is no such thing in principle of what is a fundamental particle or what is a fundamental string. Those notions depend on which range of parameters we are in. We also learned there is no fundamental notion of what is the dimension of this space. It depends on what range of parameters we are at. So we learned that all these concepts that we thought were established and fundamental were actually somewhat subjective, and depending on which parameter ranges we are at, somewhat like whether we are in the gas phase or liquid phase. They look different, but that's just because we are in one temperature or pressure region and we can gradually go from one to the other. So there's no fundamental way to distinguish them. So dualities became an extremely important way to think about the fundamental theory. I really like this drawing of Escher, which in some sense to me symbolizes the dualities that we have in string theory. So any corner of this picture, if you look at it, looks like it's a good story of its own. Here it's day and you have these black birds flying in one direction. Over here it's night and you have these white birds flying. Down here you have these fields and the black and white fields. And here you also have these fields, but it's a bit dark. It's night. And so you see that for each corner has its own storytelling, but they gradually continuously go from one to the other in a seamless way as we change parameters from down to up or from left to right. This is very much like the spirit of what happens in string dualities, that you find that in each corner there's a story going on, and as you change the parameters, these stories seamlessly go from one to the other in a way that you don't know which one is a better description. Either description is fine. You could say it's day or it's night, depending on which range of parameters you're at. But there's actually more than just whether you call it day or night, but it turns out that each region has its own virtue. That if you want to solve a problem here, it turns out this side of the problem sometimes has an easier way of answering the question up there, and vice versa. So the dualities in string theory became a magic way to solve problems. You have a hard problem here, in this side, no problem. Send it over this corner, they will solve it for you and ship it back to you. It's remarkable. So the dualities were a magic problem-solving tool. And why is it working this way? We don't have a deep idea of why. We just know it's true. We have a hard problem, we solve it and throw it back. Well, how do you know you solved it correctly? Well, many of these questions end up being mathematical questions that have an answer and we can send back and we can say we have solved it, and we can actually show it to our mathematical colleagues. So our mathematical colleagues will say, well, we have this math problem, we use physics to solve it on this other corner, we send it back to you. Does this answer fit your description? And they look at the problem and say, we haven't solved this problem yet ourselves. They look at the problem, and after a while, they say, how did you get these numbers? I have difficulty getting these, and so forth. And so they start counting these numbers, and they say, wow, the first number you calculated, we actually can prove is correct after a long work. And these other numbers, we don't know how you got it, but now that you got this other number that we had hard work to prove confirmed, we believe the rest. But how did you get it? Well, we said we use these dualities. Why does it work? Well, we don't know. It just works. So we don't have a deep understanding of why dualities work. It's an amazing machinery to solve problems, some problems which are part of the modern mathematics, pure math. And I don't mean like you have a problem that you have to crank to a computer to solve. It's not of that type. It's theoretical kind of questions that pure mathematicians would think about, and the solutions come from reasoning involving these dualities. It's a remarkable machinery. Now, these branes, these high-dimensional objects, which are these strings and membranes and so forth, mixed up with geometry, have an interesting interplay. For example, you can think about the string wrapping around a particular cycle of these extra dimensions in string theory. So you can have what we call branes wrapped around cycles. And here I'm exhibiting just a one-dimensional version of them, but it could be different dimensions. It could be like a two-dimensional membrane wrapped around the two-dimensional part of the space, or a three-dimensional version of a membrane wrapped around the three-dimensional part. And all these objects can happen, and you can imagine if you have a complicated enough geometry, and if you have this thinker toy of these objects or brains, and you can do all these fancy things around parts of the geometry, you can play a lot of games with it, and they translate, these games translate to properties of physics. So they have meaning about what these wrapping of these cycles, of brains around cycles, what kind of interplays they have. You could also have these objects interplaying with each other. For example, you can have strings coming and being cut open by membranes. So you have these membranes like chopping board, and the strings come and they kind of open up your ends, and they become open on these kind of membranes or D-branes. So you can have these kind of geometries which describe charged matter as the strings which are stretched between these other membranes. So you can have a geometric way to think about matter and quarks. So it's quite an extremely interesting way to geometrize particles. So particles would be viewed as strings stretched between different dimensional membranes, and having different number of them translate to having different forces. Could be strong forces, one of them could be weak force, one of them could be electromagnetic force, depending on what kind of geometry they have. So they have an amazingly elegant interplay between geometry and brains. Moreover, the singularities of geometry, which is sometimes headache in the context of Einstein's theory of relativity, can be interpreted themselves as brains. So for example, if you have a conical deficit, if you cut open like a pizza pie and just glue it back, you have a cone, which gives you a singularity here at this apex of the cone. So we send the light one way, it kind of looks like it's bending, because if you just put these points back together, it will continue as if going straight. So we can think about these kind of objects as particles or brains, and this is actually a geometrical way of thinking about singularities. You could also have interesting geometry, as I mentioned, about brains wrapping around cycles. For example, you can have in the internal geometry of the six-dimensional embarrassing geometries of string theory, you could have extra spheres. And then you could have these membranes wrapping them, one or this one, or maybe this one, or if you want this one, or maybe that one. Or maybe even joining two of them together. And the geometry of what kind of spheres there are will dictate what kinds of forces you get. So here, for example, the geometry of 5 spheres, and this particular structure is very specific. 4 spheres in a row and one hanging out like this, turns out to describe what could be viewed as a grand unification of forces, as a model for grand unification of forces in elementary particles. So the notion of forces become geometrized about the spheres in the internal geometry of string theory. And the relation between them, these spheres and these membranes, go via some kind of duality. So here, I was describing, let me go back, I was describing here one way of getting forces as here, and another way of getting forces was by these other sheets and the strings between them. Which one is correct? This one or the other one? Both cannot be correct. Which one is the correct one? Well, duality says both could be correct. They just don't look like each other because we have tuned the parameter. So you tune the parameter differently, they look like each other. For example, if you take this situation like these two spheres, and you think about this wrapping of this membrane around one of them, you can think about this as if you change the parameters, as if there was just a string stretched between the other two. So that picture of this string between two different brains could be viewed as this if you just tune the parameter of squeezing one sphere and then you make the other one bigger. So that's the nature of duality. So we were fooled by that picture to think that they are different. They are the same. And there are many such examples in string theory where the geometry can trick us to think they are different, but they are actually the same. It's just the choice of parameters which distinguish them, not fundamentally different. So we get more mileage out of these brains. For example, you can have these brains which are extended in different directions and they intersect, and when they intersect, they can form matter. So if you have, for example, the situation where I was describing 3 of these brains coming in one direction and 2 going in that way, you can get a matter between them which have very much like the properties of the quarks. Existence of extra dimensions allow us to create degeneracies of having the little bear, middle bear, and the heavy bear. The three generations of particles that we have could easily be now accommodated in this picture. The extra dimensions, when you have brains on one side and the red brain and the yellow brain, they can intersect on a Riemann surface, let's say, a surface like the one I've drawn here as a blue. And if you try to solve how many particles live here, it turns out you have to solve a certain equation called the Dirac equation. And the Dirac equation, once you solve it, could end up having three solutions if you have 3 units of flux through this surface. So by simple reasoning, you can accommodate at least the possibility of having extra degenerations very naturally. In fact, more is true. You can study detailed properties of how the particle get masses through these, what are the masses, why one of them is little and one of them is middle and one is heavy, from the geometry of the intersection of these surfaces in the internal geometry of string theory. And you can actually make a prediction using string theory about how these mixings or how these masses work. And here I'm just exhibiting one heuristic computation one does in string theory, where in some model it predicts some mixing of these 3 generations in this way, which is to be compared with the experimentally measured values down here as a 3x3 matrix, which are not that far from each other as an approximation. Looks certainly reasonable. And there's this other question I mentioned before, which was what was the nature of the strong forces? So the strong forces that when the problem in the 4-dimensional physics gets very hard to solve, you have to end up solving the strong coupling problem, which in this case turns out to be related to the inverse length here. So the strong coupling corresponds to this length shrinking. So if you try to solve the problem, it turns out when you try to solve it, the size begins to shrink, and so for the region of the parameters you want, basically that size goes to 0 size. And then you could say, what happens after that? Well, if you continue this, the naive continuation doesn't seem to make sense. You get these hazard signs, and so you have to do something else. Instead of that happening, string theory tells you what happens. It turns out that a new direction opens up. So the geometry of the brains gives you a new solution to what happens in the strong coupling problem, which is unexpected. So in many cases, this transition is perfectly smooth without going through any sharp transition points. And in fact, perhaps a good way of looking at it is through this situation where the geometry will have a picture like this, and as you change the parameters, the geometry changes in a way that smoothly goes from one to the other, and in some sense unifies and gives you a new picture of how you think about strong coupling in terms of a dual phase opening up. And that turns out to be a good description. And these objects, the brains disappear from one side to the other, and the dual description plays the role of the flux. Another way of looking at it is you have some kind of brains suspended between other brains, and when you try to look at the distance as large distances, the brains move to each other, and the brains disappear and replaced by fluxes through some dual geometry. The main point about this is not the details of this statement, but how geometry plays an important role in understanding the physics. The internal geometry, the same dimensions we are embarrassed by, the same 6 dimensions we are trying to hide away, are nothing to be ashamed of. They are useful now in solving problems that were difficult to do. Oliver Montanen talked about this 2-dimensional torus. That 2-dimensional torus is in fact part of this extra dimension. So having these extra objects, which were kind of being hinted at by 4-dimensional physics, ended up being already there in the extra dimensions. We just bring it back in rather than trying to hide them. And another example, perhaps a striking example, with black holes. So how do we think about the black holes in string theory? One way to think about the black hole is you take these extra dimensional string theory and wrap these brains around some cycles. And if you wrap enough of them, they become heavy and heavy and heavier. And from our perspective, they look like a massive black hole. In fact, the mass of the black hole could be the tension of these strings or these membranes times the volume of them. The more they wrap around, the more the massive you get. And they could form a black hole whose horizon could be big, and the entropy should be a quarter of that area of that horizon. This black hole could be also called the white hole, the way I have drawn it. You should imagine this as being black and the rest as being white. So perhaps one way of thinking about it is like this. Think about this red torus as symbolizing these extra dimensions of string theory. And think about this as one of these membranes. It could be a string or it could be some object like a string, wrapping around some of these cycles of this internal geometry. And this blue part is our macroscopic space. The three-dimensional space is this blue. And you put this on top of a particular point in space. So you take a particular point in space, look at these extra dimensions of string theory, and wrap a brain around this extra dimension. Of course, if you just wrap it around once, this is not going to be a massive black hole. But what you can do is to make it more and more massive. How do you do that? Well, you simply make it wrap around more and more, and it changes the geometry of this space. So let me just show you again. So by just wrapping around here, wrapping more and more here, it actually affects the geometry that we see in three-dimensional and begins to look more and more like a black hole. And so they correlate with each other. And so you can now check whether or not the way this area expands has anything to do with the ways that it can wrap around this extra dimension. So just doing some geometry computation, and you find that indeed the number of ways it can wrap around matches the size of this black hole, confirming the prediction of Bekenstein and Hawking for a large number of these black holes that we encounter in string theory context. So we find that the answer to the question of where is the entropy of the black hole hidden is that they are hidden in the extra dimension of string theory. So those same extra dimensions which were embarrassed were the places they were hiding. And so bringing it back into the game is an answer to those questions. So that's why we shouldn't be embarrassed about the extra dimension. We should welcome them and actually use them to solve problems in the context of particles as well as black hole physics. So to conclude, I want to basically say string and geometry have a beautiful interplay. This interplay sheds light on four-dimensional physics, and many physical facts have their origin in the internal geometry of string theory. Thank you. There's a question over there.
Hi. First of all, thank you for coming here and giving us this wonderful talk. I was intrigued by your CKM matrix that you had mentioned, the alpha gut that was mentioned over there.
Yes.
How is the value of that related? That was one thing. And second, what is the gut scale that we are talking about over there? Is it Planck or is it less than that to obtain that kind of a structure?
Right. So I'm not sure that perhaps many people will not appreciate the question, but the physicists who have studied grand unification will appreciate the question. So alpha gut is related to the strength of the coupling constant at the grand unified scale. So you can certainly just continue for example, in the supersymmetric models, you can continue the forces and find that they meet around 10 to 16 GeV, and of the order of the alpha gut, which is 1/20th or so. And so you just put in that alpha gut in that formula. That's what we are doing. And that CKM estimate I was showing was not supposed to be meant as exact prediction, but order of magnitude, really. So it is surprising that they matched so well. It wasn't meant to match that well. This matrix that is prediction, and that's actually a more interesting story. So when we predicted it, we get the general features of PMNS matrix, but we also predicted that theta 1,3 was not 0. That was at the time where the favored value was 0. We predicted that the mixing angle between the first and third generation of neutrinos was around 0.2. The recent experimental measurement of last year turns out to give you 0.15 as the answer. So that could be viewed as one of the first predictions where our prediction, which was 0.2, was at the moment where we made the prediction was not among the favorite values, but later it became. So that's a better story, perhaps.
Can you please elaborate on the parameters that have to be changed for higher dimensional strings? What
are these parameters?
Yeah.
So these parameters could be viewed as the geometry. So for example, you take a circle, you can choose the size of the circle. So these parameters generally are of that type, shapes, sizes.
Okay. A quick question. Can you please explain duality in the context of causality?
Duality and causality, what do you mean? The duality and causality are two different questions.
You explained that in duality problems, the problem can be solved on one end,
yes,
but it cannot be solved on the other end.
Yes.
So in the context of causality, where the effect precedes the cause, or succeeds the cause, can you explain in that terms? Because that's
it's not so much, it's not cause and effect story. Let me explain it in a different way. Suppose you're trying to solve, how could I say it? Let me just give you a simple example. Suppose you have a chessboard and you want to put some black pieces on this chessboard. And suppose the chessboard is 1,000 by 1,000 chessboard. Not 8 by 8, but a huge chessboard. And you ask, you want to put 995,000 pieces. How many ways can you put this? Looks like a complicated enough problem if you want to really count by one, but the inverse problem is much easier. You just say, oh, I can imagine the pieces which are not full. If you're allowed to put these only at distinguished places, the inverse problem is easier. So I just say which ones are empty. That's easier to count. This is somewhat like that. In other words, in principle, on either side you could solve it, but one side looks harder than the other side. The other side is much readily available. So it's that kind of duality. It's not like the problem does not have an answer on either side. One side is the right way easier way of answering it.
Right, we often hear much about these theories being useful for explaining black holes and things like that. Closer at home, do we find these theories useful for explaining things like anomalous expansion of water, snowflakes being different in so many millions of patterns? Is it useful to interpret some of these things closer at home?
Well, specific questions about specific condensed matter physics questions or aspects of that are, of course, farther removed from this. I mean, in principle, one could, but I don't think these techniques are particularly relevant for that domain. It's like saying, can we if we describe physics, fundamental forces, can we describe how society works? No, in principle, maybe, but I wouldn't really use that to describe our conversation now as coming from fundamental forces, even though in principle it does. So it's the same sense.
In general, when I read about, I'm a non-physicist, so in general when I read about string theory and other things, right, it seems like a very nice way mathematics to explain certain things. One of the fundamental questions that always come up is, are there falsifiable experiments you would do, either to explore other dimensions of string theory, or in terms of even brains, we talk about how gravity can be explained through brains, right? Are there experiments that we can do today that would either falsify these expectations or satisfy?
Okay, so you have a very good question. Certainly, science is truly falsifiable, but your question had also a second part. You said, can we do experiments today?
Right.
That's not happening. Then if you don't see some other degrees of freedom coming into play, like the kind of things we see in string theory, then string theory is out. So we better be able to see some things like the kind of objects we see in string theory. Now, having said that, I have to modify it slightly. It turns out that the string theory has embarrassment of riches as far as possibilities. So you have a huge landscape of possible solutions. Now you have to say, which one of these solutions are we in? We don't know yet. So, but nevertheless, we expect to be in one of these solutions. So if you do experiments and don't see anything interesting, then string theory is out. Thank you very much.
There's some tea outside on the other side.